Good evening, welcome back to the Code Athlete. Today I want to go over problem 4 of round F 2021 in Kickstart, Google Kickstart competition. So if you've seen the previous videos, I already did the trash bins, the festival and the star trappers. And now problem 4, graph travel, is possibly the hardest one, as it's usually increasing in difficulty with these competitions. Just a heads up, in a few days there will be round H of Kickstart, so I will try to record myself there, participating live. It's quite early here in Germany, so I'm not sure if I will manage to actually get out of bed, but I'll try. And if you want to practice for that round, have a look at my round G video, which I got 4th place, I believe, in Germany and 118th rank worldwide. That was a good round for me. Maybe you can learn something there. Or in this video, let's have a look at the problem statement. So the problem reads, Anna lives in a magic country A and she is studying at a magic university. Today Anna wants to collect magic points in a special space. Space has n rooms. There are m corridors connecting the rooms. Corridor J connects room XJ and room YJ, meaning you can travel between the two rooms. The each room contains AI magic points and is protected by a magic shield with properties Li and Ri. To enter the ith room, first you need to get to any room adjacent to the ith room, connected by a corridor through rooms with already broken shields. And you have to break the shield to this room, but you can break the shield if and only if you have between lower or left and right magic points inclusive. After you break the shield, you will enter the room and automatically collect the magic points assigned to this room. The room will not generate new magic points. The room will also not generate a new shield after it if it's broken. So you can freely go back to every room with already broken shields, regardless of the amount of points you have. Anna starts with 0 points, and her goal is to find a way to collect exactly k points. She can start in any room and end in any room. The room she chooses to start in will automatically have its magic shield broken, and she will automatically collect all the magic points from this room. After inspecting the map of the rooms and corridors, Anna thinks the task is very easy, so she wants to challenge herself with a more difficult task. She wants to know how many unique ways there are to reach the goal. Ooh, 2 ways are different if their unique paths are different. The unique path is the order of rooms in which she broke her shields. If you visit the rooms in the order 1, 3, 2, 1, 3, 5, 3, 6, the unique path is 1, 3, 2, 5, and 6. Okay, so the number of unique paths, or the number of unique orders in which you can collect the points of the rooms. Interesting. Let's have a look at the input, or at this test case first. In the first test case, there are 4 different ways. Why don't I write the magic point numbers here? So test case 1, 4, 3, 3, the first line is 4, 3, 3, yep, right. 4 rooms, 3 corridors, and k is probably then this number of points she wants to have in the end. 3. And then we have the 4 rooms and the 3 corridors. From 0 to 1, from 1 to 2, from 2 to 3 are the corridors. And the rooms have number of magic points, possibly the first value. No, the last value is the number of points. So each room in this scenario has 1 point. And the ranges of points she needs to break the shields is 1, 3, 1, 1, 2, 4, 2, 3. So in this case, if she starts here, she gets 1 point, and she can go to room 1 and break this shield, no, this shield, sorry. Then she has 2 points and can break the shield of room 2. Then she has 3 points and is finished. Here it's the other way around. I'm thinking if we can do just a depth first search. Let's look at the sizes of the problems. So the bigger problem, bigger problems. No. Bigger problem has only 15 rooms. And the number of edges, of course, is given by the maximum amount you can have in a complete graph with n nodes. So this is basically if you connect every room with every other one, this is the number of corridors you could end up with. And now I'm thinking 15 rooms. Then the worst case, if every room is connected with everyone, we have what we have 15 possible starting locations, and from there we have 14 possible follow-ups, and then 13 rooms, 12 rooms. Of course, there might be break conditions, like we can't walk in all 13 for every of these combinations because of the shields or because of the number of magic points we want to reach. So if we have enough, we would stop. But in the worst case, I would say we have to visit every room to get all the points, because that might be our target value, and it might be possible to get from every room to every room. And then the worst case is, like, I'm writing here 15, but the problem is n rooms. And 15 faculty seems like already way too big. Yes, so this is 1.3 10 to the power 12. That is too much. So what can we improve? I mean, we really need to think about how to improve this worst case scenario. So we could have 15 rooms and all are connected. Shield is, let's say, from lower equal 1 to upper or right equal to 15. Each has 1 point, so the points is 1 for each room, and k is equal to 15 as well. So this means we need to visit exactly each room to get all the points, to get 15 in the end. And it also means it doesn't matter actually which number of points we currently have, because we can break any shield at any point. And for this scenario, the solution would actually be 15 faculty. which tells us this is a large number, which we potentially need to print as an output, but which we can't get by simply counting. So we need to take real shortcuts during the construction of this number. And the real shortcuts, where are they? I'm thinking if it has something to do with these shields, if we can like pre-process the shield values. I have really no good idea here. The optimal solutions, or the number of solutions, are all over the place. Sure, okay, it's easy enough. We can always split the graph into its non-connected components and count for each of the subgraphs. I mean, that's easy. And then we just add it. So here it's basically 2 for this connected component, 1 for this, 1 for this over here. So in total 2 plus 1 is 4. Yeah, sure, but yeah, the shortcuts for this. This is just 10 to the power 12. That is too much. I'm thinking dynamic programming. Because tell you what, at any given moment, yeah, dynamic programming, this might be a good idea actually. Because at any given moment we have visited a few of the rooms and we haven't visited others. So basically for every room we have the switch, is it visited or not? And for 50 rooms or for n rooms, this means the state space, which rooms we have visited and which we haven't, is 2 to the power of n. Or 2 to the power of 15 is roughly 30,000, which is a quite small number for a computer. So this is something we can handle, even in memory. So we could make our big dynamic programming table, and this could be the number of rows, for example. But how would you construct this now? Because I'm now thinking if this table needs another dimension, maybe possibly the number of points we have. The different amount of points we can have is actually also not that big. It's the same even, because for every of the states, which rooms we have visited, we just sum up the points of the rooms. And this is the amount of, oh yeah, it's actually one-to-one correspondence, I'm just realizing, sorry. So for each of these states we can exactly compute how much magic points we already got. And from there we can compute which rooms we can visit by breaking shields. And what we possibly want to count is let's say we want to count how many ways there are to reach a specific state of room visiting, not of ways getting k points, but for a given state, let's write in our dynamic table how many ways there are to reach this configuration. And that seems sensible. We can initialize this table by saying, okay, there's a state where we haven't visited any rooms, and there's I guess k is, yeah, you can see k is here larger than 0, so we have to at least visit one room. Anyway, that drops this empty combination we don't really care about, but we could say for the state where we haven't visited any rooms, there's one way to get there, because it's a starting position basically. And then for all the states, for all the 15 states where we have visited, let's say there's a state where we only have visited 1, or we have only visited 2, or only visited 3, there's each one possibility, because, well, we have to start in that room and that's it. Now, if we're asking how many ways are there to get to state 1, 2, we can say, okay, to get to 1, 2, we either have to be, the state before has to be either 1 or either 2. We can check if this is okay, because when we have, for each state, we can compute the number of magic points we already collected, and we can check if it breaks the shield for the left out room, which in this case would be the 2, in this case would be the 1. So we can check which of these actually contribute, and then we know this is currently started by 1, then we can sum these up. So if both contribute, this would have a 2. And this works even for more complicated states. So let's say we have the state 1, 2, 3. This can have up to n rooms, of course, but that would be the last configuration. And there are basically 3, because either we have to add room 1, add room 2, or add room 3. And if we add room 1, we are coming from 2, 3, or we are coming from 1, 3, or we are coming from 1, 2. And again, we can check if all these which of these connections are valid, cross the ones out that are invalid, and then sum these up from our table. Now, what is the complexity of this? So checking if this connection is okay is basically, let's say, constant time. Because these sets are never larger than 15, so it's quite easy to check. To take the sum of these 15 values and then check if it's inside the shield region of this room 1. So each of these checks is basically constant time, and we have, or let's say in time n maybe, and we have up to n checks for every state. So, and we have 2 to the power of n states, so it's roughly this runtime. And I will give you an exact number for this, but I suspect this is actually fast enough. Yeah, so this is 7.3 10 to the power of 6. Sorry, I'm German, so we always make commas here, but American people would do a decimal point there. And that is totally fast enough. So I will start implementing this. Let's see how it goes. I have to watch out that I'm actually processing these in this order from low visit counts. Here's each visited only 1 room, and then all the combinations where I visited 2 rooms. And then all where I visited 3. Oh yeah, let's see how it goes. I have to think of something there. Let's read the input. And lines have LE oh N, sorry. We have only 15 rooms at maximum. And AI. And then we have the X and Y, the room indices that are connected by a corridor. And there we can have potentially quite a lot. Actually, let's save this in a matrix. It just says if it's connected or not. Okay, so we have read those values. Easy enough. Now I have to iterate over these states, starting with the empty one. what is the best way to do this? I think I have a tool for this. Selection tools. I actually found out that there is a built-in. So I'm back. Sorry, I had to hide there something. Personal bookmark bar. Yeah, but I found what I was looking for, an experimentation, and I remembered now how it was used. So I can plug in basically, if I want to have basically a section for, say, 3 rooms out of 15, then I put 12 zeros and 3 ones, basically as a string or a list of numbers, integers or bools, and let it iterate with this next permutation. It will give me all the different permutations, whereas with elements being equal, the zeros and the ones, or the Boolean values, whatever, it will skip those if they're equal. So that's quite nice, and that's how I will get every permutation. So let's go on with the code. Result is an integer, we set it to 0, and first iterate over, we have to, of course, initialize our state space. We will signify it via a number. Yes, I think so. Yeah. We have to initialize this. I really have to learn how this works. I see, so here's maybe a tip which I see often. So a lot of pros in competitive programming use these arrays, and I more often actually use my vectors. So this is just a shortcut for this type. And the nice thing is, for the vectors, I know I can call, like here in this case I wrote it myself, but if it would have been a vector, I could just say clear or resize, and say it has to be size n and the values have to be 0 or so, false in this case. And there is probably fill or something. Fill states with 0 or so, I don't know. And now the number of rooms we have visited goes from 0 to n inclusive. So how does this next permutation work? Needs a range. Well, I will use a vector for this now. Call this n number visited, so this is then visited. N rooms, let's set them all to false, and where we initialize our permutation. Now I have to check How long does this go? Because this ends somewhere. Not sorted in the beginning. And then here I have a shortcut again. Let's just show how this works. Thank you. This needs also the start and end iterator. Yes. Oh, and fill, of course, that was something. Okay, so I just looked it up. It's this syntax, the number of values and the value I want to fill it with. And then I just remembered that I should set this 0 state to 1. Otherwise we would only sum always zeros to more zeros, and we should probably start here then with 1 visit. So we don't need to recompute the 0 visit case. Let's have a look now. So yes, here for case 1, we had 4 rooms. We can see first we visit these 4 combinations and all the 2-room combinations, which are 6 in total, yes, and then 3-room combinations are again 4, and then the last one. So we visit them in the right order. That's very good. Now we need to compute the ID. Now we have the IDs, so converting it basically into a binary number. This can probably also be done better, but I don't care. And it doesn't matter which way you... So right now the right bit in this representation is the highest one. That's fine. These look okay. And now I need to... Let's also compute the sum of points for each of these states, just to make it faster. We fill that with 0 again, which in the special case of having visited none room is also correct. And here we can now actually use this information to also update the points. Oh no. Actually, after we have computed the ID. Like this, yes. Now for each of the rooms that go in, I have to check if I can actually take that move. Yes. So we're checking for again if we are coming from which room we are basically coming. Well, what's with the start rooms? And we're not coming from any room. But this is fine, we're coming basically from a specific state. Yes. So if this is not visited, we can directly continue. Otherwise, E is the room we just are going into. Ah, wait, I forgot something. The shields. Oh no, it's fine. I need to get now the ID of previous, yes. Previous ID is then equal to ID XOR this. Let's log this as well. And now we have the previous state ID. Now we can just check. If this connection is okay, and we need to update our states. Yes. If previous ID equals to 0 means this is an empty state room where we always guarantees that we can get to any room. Or the other condition is that the points we had in the previous room, which is our point sums from previous ID, is in the inclusive range of the shield values, which needs to be both tested. I is the room we're now going into, so those are the shield values we have to compare against. And this is a condition if we can go into the room. And if we can go into the room, well then the states for ID needs to be added by the states from the previous ID. And in the end, we can actually look at all the states. And let's also look at the point sums. let's go to test case 1. This is ID 8. And we can only bin gone to 3, and the previous ID is correctly 0. Yes, and next visibility again, previous ID 0. That's all nice. Let's look at here. So the previous ID for these is either 8 or 4, which it finds here and here. Yes. Depending on if 2 or 3 was visited. That looks all good. Oh, and my print routines don't work anymore for arrays. That's a bummer. But let's just hope that it's right, because now the result variable is actually quite easily checked. Just have to check all our states. There are those many. And if point sums for this state is equal to k, well, then we have found a valid room selection. Now we just add up the ways we got there, which we collected in the states variable. And it's the wrong solution. But only for test case 1 and 2, interestingly. So I really need to log those state variables. So ID 0, there's one possible way to get there, and the point sum is 0. That's correct. ID 1 was where we visited the leftmost room. If we look at the task, the leftmost room had 1 point. They had all 1 point, and shield value is 1, 3. Okay. So point sums 1 is correct. States 1, there was one way to get there, sure. For 2, again, this is only visiting a single room, so these two values are correct. For 3, we already visited the first and the second room, so we have a total point sums of 2, and there's 2 ways to get there. Is this correct? 0 to, we can go from 0 to 1 or from 1 to 0. Both paths are possible, as we can see in this image, so that seems to be correct. 4 is again just visiting 1 room, 5 is again visiting 1 and 3, or 0 and 2. And it says there's only one possibility to get there. Can start here, and then we cannot get into this room, but we can start here and get in this room, so one possibility is correct. That was 5. 6 is room 2 and 3 basically, so point sum of 2 is correct. States 1. Can go from here to here, yes, because we have 1 point to get in here, but we can't get from here to here, so that one is also correct. 7 is the rooms 1, 2, and 3, so in total 3 points, and there are 3 ways to get there. And it says 11 or also 3 ways, which total makes 6. Which is really what was printed. No, it was actually printed 10, right? Yes. So let's check 7. First 3 rows. With 1 possibility, 2 possibilities, 3 possibilities. So that seems to be correct. There should be a 0 where the sum is 3. 11 is a binary representation 1, 1, 0, 1. So it's 0, 1, and 3. From 0, 1, and 3. Where it here shows us no combination at all. Why actually is that? 0, 1, and 3. I think I haven't understood the problem, because why can't I go here? Oh, I have to check if they are adjacent. Yeah, sorry. So we can start anywhere, or we need to be able to kill the shield. And now it comes that we need to be able to get from any of the previous rooms into this room. So we need to compute a connectivity thing here, which actually requires us to iterate over all these n values. But I think that should be fine. If adjacent I to j and visitor j, then connected is true, and we can break this for loop. And we check here for connected. Let's do that first. Still wrong? Oh, this is a mutation which does not work. Yes, and we got the right solution, and I suspect that should work now, because it actually is quite a simple problem. I'm surprised, actually. And should be definitely fast enough, I would say. Because now let's have a look. So this, in combination with this, so this for loop, which iterates over the number of rooms, in combination with this do while loop, which is going over the iterations, just gives us the 2 to the power of n combinations. We just split it up in 2 loops because we needed the special order from counting all the states with only 2 rooms visited, then 3, then 4, and so on. But in total, these 2 loops are just 2 to the power of n. And inside here we have n, another n loop, so 2n, and then this n loop again with an n loop inside. So this is n squared, which is then more dominantly than these 2n. So we have in total our n squared times 2 to the power of n combination, which is fast enough and got already evaluated and is correct. So yeah, forgot about the connectivities in a graph problem. That's really a stupid mistake. But I hope I made clear how this works, and the implementation didn't got too messy. It looks quite fine. I really should look up again how the pros are doing this initialization, because I think they do some kind of mem operation here, which is probably more efficient. And I don't know, this seems kind of ugly that I have to specify again the number of elements. So I will try to look that up and maybe also adapt my LG thing here to print arrays nicely. Some to-dos for me. Otherwise, have fun preparing for Google Kickstart Round H in the next few days. It's basically on the upcoming weekend, and we'll see each other then, I guess. If you liked this video, please leave a comment, a like, subscribe to the channel, and ring the notification bell. Would make me very happy and helps me let this channel grow a bit over time. Thank you and goodbye.